So if you're done, then it is done. Let's start with my next example, which will be YOLO. So I asked all of you to download the YOLO from your YOLO.zip file. Go to your YOLO.zip file is available in your Google Drive. So download it if you have not downloaded and unzip it. Download it, then you can unzip that. This will look like this. Will look like this. It will have a configuration file. It will have the already trained model weights, and it will have the names as well. These are the objects that it is capable of detecting. Okay, uh, person, bicycle, car, motorbike, aeroplane, bus, train, truck, etc., etc. These are the things that it is capable enough to detect. It's again a trained model already, and we have to just understand that how to use this YOLO effectively. To No problem, I will upload that. You can download just any objects, any images will work here. Student images are not among. No, whatever the images are not there, let me upload. You can download. These are simple Google images. Okay, I have uploaded the images separately. Whatever the images are missing, you can download it and you can try them. Let's start with YOLO part. The theoretical part about the YOLO, I'll give you the explanation about it tomorrow. Today we'll be only talking about the how to use YOLO for detecting the objects on the images. And yeah, this will be our second last project. After this there will be only one project left, and that will be related to our uh, the unit part and doing the image segmentation. Okay, let's go ahead and let's start with YOLO, which means it stands for you only look once. This is a single page detector. Let's do import CV2, import numpy np, import OS, import system, import matplotlib, pyplot, splt, config path equals to eopencv, YOLO, YOLO version 3 configuration file. Just like the way we train our model, so it saves the weight. Like it happened here, right? We are saving the weights of these trained model under .hdf5. Uh, the YOLO saves the trained model. So YOLO is just like using already trained model, and this already trained model are saving their weights here. So weights equals to, take the path eopencv, folder name is YOLO. Please download this file. You will find under the Google Drive, and unzip the file. Don't try to read the zip file. Let's get the labels, which will be available as a file format named as coco.names, eopencv, YOLO, coco.names, and let's read them separately. Let's read So 80 different objects it is capable enough to detect. We are having a YOLO V4 as well. You can try to use the same thing with YOLO V4 as well. Next, let's take here some of the variables that we require. First is confidence value, which will be 50%. Threshold value, which will be again 50%. And IOU, threshold value will be zero point 0.5 again. What is IOU? Intersection over union. IOU value used in object detection to measure the overlap of overall predicted actual box of object. Let me try to help you through the help of Google so that you can get at least a basic overview that what exactly the IOU stands for. So this particular thing that we are talking about, structured data markup helper. Oh God, from search engine it has changed its name. Seems like okay. Um, I was saying like IOU YOLO. So when we are talking about this, you see that what exactly we are trying to do. So IOU is something like this: that two objects are, let's say, are detected, correct? Which will be detected like this. So IOU is created by this one, right? This green is your truth value, whereas the predicted region is the red region. Now, to take the difference between them is called as your IOU, and this IOU should be greater than zero point 0.5. Then only that object will be considered to be detected. Otherwise, we will say that it is not detected properly. Okay. Uh, just try to understand a term that like this. Say the green is the actual predicted region, whereas red is the predicted value. IO and the difference between them is the selected region, which will be this, and that selected region will be calculated by a simple formula, that is detected or predicted box versus the actual box. So region between them divided by the union of both. Okay, so hope this makes sense. What is IOU? uh, it is basically intersection over union, and intersection over union is calculated by first the common region between the predicted region and the actual region divided by union of actual and predicted region both. Okay, so this should be again 50% around. So that's the value. Object detection to measure the overlap of overall predicted value. You can say measure the overlap of the overall predicted actual box, which is we are keeping it as 50%. To have hard on it, you can increase this threshold. So in that case, less object will be detected. So I'm keeping it as just 50%. Any object which scores IOU less than 50% will be not detected. So these are some of the initial settings that we are doing. Now let's build our model using dense neural network DNN algorithm, which is an inbuilt algorithm to OpenCV. Build a model by loading weights of YOLO V3, loading weights of trained model YOLO V3. Net equals to cv2.dnn dot read net from darknet. Provide here the config path, load the weights, and create your algorithm. Now, different objects should be detected as different colors. So, different colors for different objects. In order to do that, we will go for colors equals to numpy dot random integer 0 to 255, size equals to length of labels, comma 3, d type equals to unsigned integer 8 value. Different color combinations will be created randomly. Okay, moving ahead to the next part. Okay, here in this case, so every time you will execute every according to the labels will have different color combinations which will be created. Now let's create a model. Create a model which will be given by def model underscore output. We'll have the path name. Start with my image equals to cv2 dot I am read. We'll start with my path name. File name equals to os dot path dot base name. We'll start with my path name. Okay. So we will got here my image name which will be passed. It will also read the file name directly from the OS. Okay. Once we got all these things, we have to provide the location of the path, and from there it will try to start working on it. Okay. So in order to do that, it will be reading the file name and the extension. Extension is of course not required. In order to do that, we will simply write here file name variable dot split by dot, because extension will be separated by dot value. So here we come with my file name and extension. Let's get the height and width is equals to image dot shape colon to blob equals to cv2 dot dense neural network dot blob from image data 1 divided by 255 and 0. Start with my 416 cross 416, that's the standard input shape. And because we will read the image as using cv2, so we know that your red and blue will be swapped, so we need to swap it back to get the original color. Okay, so from the image a blob will be created, and that will be my input. This is nothing but it is talking about the image data. Blob is nothing but it is your image data, and we are making sure that all the images data are divided by 255, so that's pixel normalization, and image is reshaped to 416 cross 416. That is a standard shape for the YOLO, and we are swapping the position of red and blue because the OpenCV reads the file as uh, swapping the position, that is BGR. So we need to get back to RGB. That's why swap RB equals to true. So we got here my image data, and now from here we need to set our dense neural network. Set dense neural network, which goes like my YOLO model layer. In order to do that, in order to do this set part, we will start with my net dot set input blob layer ln net dot get layer. Okay, after getting the layer names, let's try to get here ln, that is my layer, equals to ln I of 0 minus 1, and we will iterate here for I in net dot get unconnected output layers. Now this ln thing, this is basically to get unconnected output layers. This is used to obtain indexes of, let's get the coordinates of the boxes and the confidences and the detected class IDs. Let's initialize them as three list. Okay, either this part will work or there is one more thing, and that will be related to your ln. In this is due to the change in the version issues, so it could be like ln I minus 1, or it will be I of 0 minus 1 for I in net unconnected layers. Basically, we are on creating all the layers here. So either the first part will work or the second part will work. We will see that if how the error comes in. Okay, so we will discuss about the yellow thing tomorrow further. Okay, we will complete this thing. Maybe most probably our things will finish by tomorrow. If it doesn't finishes, then maybe an hour of Tuesday session will be required to finish everything. Otherwise, I'd expect to finish everything by tomorrow. I will upload one more data set, which will be, of course, related to the images. Let me upload that. Meanwhile, you all finish everything. There is no error in the program. Check again. I have uploaded the code. Check the code again. And yes, right now don't execute anything because obviously this is not done yet. This function is not finished yet. Take your path properly where your YOLO files are present. There has to be some mistake, right, that you might have committed. If a code is working in my case, it should work in everywhere. Passing your config path and the weights, the problem has to be there in that. There is no need to install anything. If your OpenCV is installed, it is basically taking, it is an inbuilt method to the OpenCV package. This darknet is an inbuilt function in my OpenCV, so no need to install anything. My version and your OpenCV version is almost similar topic. So as I discussed, today I'll be talking about YOLO topic, and we started with this particular example. Also, like to remind you that if you have not downloaded the latest file which was uploaded yesterday related to our okay, so let's get started with my model output. If you look at here, we are talking about so we got here my layer names as you observe, and we also got here my get connected unconnected output layers. With my layer underscore output will provide us the net dot forward, and we initializes three list which will store the boxes, confidences, and the predicted IDs. Let's go through the value here for okay. Let me walk you through. Like we are creating a function which will return me three things: the boxes coordinates, the confidence, and the class ID. What are these boxes basically? So let me tell you how YOLO works. So for instance, if I'll go with my object detection part, I am talking about here to let you understand that what exactly is the boxes means. Okay, so the boxes are your region. Okay, the selected region where the predicted region, in fact, you can say. So here is your particular example of boxes. How does the boxes is detecting? Like you can see here, one of the important, basically, what is the use case of this? Use case of YOLO will be real time object detection. This is one of those algorithm which helps us to particularly perform the object detection on the real time video or on the images, etc. Let's pick any image here. What it will do is it will try to, let's say I'll take an image, and in that image we'll have different objects in it. Okay, I'll take that classic image of YOLO example, that dog example here. Okay, so the first step that you will observe YOLO performs is that it will convert this entire image into an S cross S grid. Okay, it will take here, say, I'll go with even more lighter thing. Okay, I think this will be visible. So it will try to create S cross S grid. Instead, let's do it as a line. It will be easy for us to draw then. Okay, let's assume that this is the line here that is getting created, and we'll have a color here. In this case, maybe we'll go with a yellow shade. Okay, fair enough. This is your example data set, and the first step that it is gonna do is it is gonna create a grid. Okay, let's assume that this is the first grid that got created, and now it will be horizontal. Of course, we need to divide it into this. So in this case, you can observe that we are having one. This is all divided here, one, two, and so on. It will continue doing it. So you can see that we are placing it, and this is how the grids will be formed. Now each grid will have different objects in it, isn't it? If you will look at here, each grid is having different objects inside each box. So the predictions will be made now. Okay, and it will try to know that. So each cell in which the center of an object, for instance, let's say center of the dog resides, is a cell responsible for detecting the object. So there will be each cell which will basically play an important role. And in this case, let's say we have got an S cross S grid. S cross S grid on input is created. And now look at here, each box, each particular box that you observe here, this will go to the algorithm and it will be responsible for detecting the object. So each cell is responsible for detecting the object, for detecting the object. Here each cell will predict the B boundaries, boxes and confidence score. And that is what I was talking about. Each cell will basically predict here, will predict B boundaries, boxes, and you can see that what exactly the boxes means now. Boxes and a confidence score for each box. The default for this architecture is for model to predict two boundary boxes. Now each box will predict either 1 or 0. Sorry, each box will predict confidence score from 0 to 1. Okay, we will get the center of coordinates as well. Now these confidence level capture the model's certainty that whether the object exists in the cell or not. Basically you will get the confidence score, as well as you will get another thing, that is your, what I've written, the third thing in the code. The third thing in the coding was related to class ID. So let's write the class ID here for class ID, which will basically help us in identifying which the confidence score is for which particular label or which particular product. Sorry, which product, which object for class ID. For different class IDs, the different confidence scores will be predicted or displayed here. The coordinates will be the return type in this case. So each of these boundaries boxes are made up of five numbers, five values, which are your x and y coordinates that represents the location of center of predicted bounding box. Next thing that we need to understand is the IOU region. So these confidences that we are getting is basically representing your, will be equals to IOU upon union of intersection over union, which is the area of the intersection of the predicted and the ground divided by the area of union. Let me write here. Confidence will be given by IOU, which is basically area of intersection of predicted and ground truth boxes, and will divide it by area of union of the same predicted and ground truth boxes. This is can be easily understandable by Okay, this is let's say this is the actual, and this is the predicted region. So IOU is given by this shaded region here. Imagine that there is an object here. In terms of if I'll try to put around this, so let's imagine that we are having two shapes. One is this, which will be given by, let's say, blue shaded value, and this is the, let's say, ground truth or predicted value. This is predicted, let's say. Okay, this is let's say predicted value. So I'll just color it as red or something. This is my predicted region. Whereas we'll have the actual value, and actual value will be, of course, in this particular part where the overall dog is under this box region. So you can see the differences between them. You can see the difference here. Just okay. So IOU is this. IOU is this particular region, which is the area between both of this. Okay. So I'm hoping that you are understanding it. That this blue is your actual. Even I'll try to put some other color maybe. I was saying that this is gonna be your actual, and this is the predicted. So region shaded between this is what called as your IOU. Okay, and the union of both the boxes, this decides your just divided by union of both the boxes overall, that will be the deciding factor of that we are trying to get how the confidence will be computed. So you can observe here that we are trying to take the overall union of both. Just take the union of both. This is known as your confidence. Once we come to know about this, let's talk about the next thing, which is given by. Okay, this will also return me the height and width as well. So yeah, that's how YOLO architecture works. Okay, one more thing you need to understand that the algorithm that has created, it has been trained to an input size of 448 cross 448. This is the input shape which it has used. Okay, after doing all this, let's move back to our coding part. So that is what basically we are trying to do it in the coding section here. So different outputs will be there. So for each output, so for output in layer underscore for detection, let's get the scores which is given by 5 colon. That is first 5 entries. We'll get the scores of first 5 detected value. Of course, this will be a multi-class classification, multi-class probability for its class label will be detected. That will be somewhere like this 0.05, say 0.0, sorry, 0.9, 0.05 again. If you will sum them, it should be 1. Now let's pick here my class ID will be given by np.argmax, that is argument max of its course. Let's get the confidence which is given by scores of different class ID. Let's start with if confidence is greater than confidence variable. Let's detect the box which will be given by detection colon 4 and will multiply with np.array, and this will contain my height, height of the objects, the box basically. So we have selected here four values and these are labeled as your WH. Now we know that the coordinates that we have got is the center coordinate of the box. These are your center coordinates. So center coordinates of box, along with that will get total width of my object, and along with that we'll get total length of the object. Let's have the detection as center x, center y, width, and height of the box. We have saved it under the box variable, so let's read it. And let's make sure that it is converted into an integer data type. We are basically trying to take this one. Okay, it's already integer, but we are ensuring that it is an integer data. If there will be any floating term, it will be also typecasted to integer. So basically, the detected region will be your value of the box center position, and those are these coordinates. So different object will have different center values. Remember that of box, which is basically your detected object or detected object. So I'm hoping that it is making sense. It's very simple that we are iterating through the different objects of your images, and whatever the detection it has made from the output, we are getting the scores for it. And from the first five scores, we are applying argument max. We are taking the top five detection. You can take let's say six or seven as well. That doesn't matter because out of that it will choose which is. All right, participants able to hear me back? So we got here my central values as you can observe. Let's draw the boundaries around it. Center x minus width divided by 2. Got here y. Start with my center y, width divided by 2. Boxes dot append. Start with my x and y value. Int value of width and int value of my height. Let's go with my confidences dot append. We take here my floating term of all my confidence value. Let's begin with my class IDs dot append and pass here the detected class ID. So as I said that this part is all about the detection, which are the box coordinates, various confidences, and the class IDs. So multiple boxes will be created. Multiple boxes coordinates has been created here, as you can observe. That will be stored or appended in the list by going through the different outputs. Then similarly confidences will be taken and the class ID will be taken, and they are all stored in the list form. So return type will be a list, remember that, which will contain multiple boxes coordinates, which will contain four value x, y, that we created here. From the center we have just subtracted the, I mean, we have just adjusted the width and the height to get the proper value. Okay, one second. One thing looks like missing in this case, and that will be related to the, and we are just dividing the width, isn't it? So we can try to make the adjustment. So which should be the height? Can you help me with that? How the height should be playing an important role? Height should be adjusting the x, or sorry, it should be adjusting the x-axis, or it should be adjusting the y-axis. How we should able to find the x-axis? See, we are at this position, right? Try to understand the logic that the algorithm is detecting this particular position, the center position of the object. Let's say there is a car here, right? So it will able to find the coordinate for this in this box. It will able to find the center value. Now using the center, it will try to detect the height and width, correct? So according to that we can draw the boxes. This we have got, and this is related to your, let's say we have got it as w and h. Okay, height and width we have got. Yeah, so we have got here the height and width. Let's say that it is coming out to be h comma w. Now from this we need to adjust the position so that we can get the starting value, like it is starting from this, right? So how to get to this position? Okay, now from the center of the car we need to find the position. Okay, so that we can draw the boundary around it. So tell me, this is height and this is width. So how to get to reach to this x and y value? We should able to reach it with the help of x will be affecting what? Height or width? Height will be adjusting the y value, and width will be adjusting the x-axis value. Okay, so that's the logic by which we have got our model's coordinate. Okay, done. Now we need to, now this is gonna return the coordinates. Let's make the detection. Define again function detection underscore recognition. Provide your path name. Pick here my images, which is given by opencv2 dot I am read path name boxes confidences and the class IDs. Model dot output, and let's take my path name. Pick my IDs cv2 dot dense neural network dot boxes. This will take boxes confidences score threshold IOU threshold, which is zero point 0.5, of course. Scroll threshold is also zero point 0.5. IOU threshold is also zero point 0.5. Font underscore scale is equals to 1. Let's do Okay, now before we start making the detection, we need to check what is the total length of the detected values, which is of course getting coming up from the ID axis. So we need to ensure that it is greater than 0, then only it should go for the next thing. For I in indexes, we'll make sure that it is flattened as an array. Go with my x and y value, which is equals to boxes I 0, boxes I of 1. Similarly, we get the width and height, boxes position number 2, and this would be the index position number 3. Color, we can choose it from the different options of the color IDs that we have taken, which is saved here at the beginning. From the colors option, we can take it. Now, different color IDs will have, different class IDs will have different colors in it. I'll convert them into a list. Int of C for C. How to identify center of the car? Algorithm is predicting it, no? That's where the YOLO is doing its job. This algorithm that we have created, first we will take the input data, which will be your image as a blob. We got the layers here. We connected the neural network. We created the layer output, which is a feed forward neural network, and then that's it. We are making the predictions. So from the layer output, we'll be getting different detection. Okay. So those detection will go through each and everything, and we will able to observe that okay, three things are there. As you observe here, that we are getting the scores from the detection. So we are choosing top 5 scores, which will be obviously in terms of distributed probability. Argument max, as you know, that returns you the index position of the maximum score. So with that, we will able to know which class ID is predicted here, and let's say position number 1, position number 2. So total 79, 0 to 79 will be the total class IDs, which indicates total 80 objects. These are the 80 objects. So according to that, your class ID will be created, boxes are created, and confidences will be created. And that's what we are returning. Now we are just using the return type to draw the particular regions here. That's it. So we are storing the color, and now we will simply draw the rectangle, that is cv2.rectangle. Take your image x comma y, x plus w, y plus h, color equals to color, thickness equals to thickness, text equals to f, labels, class IDs of I, confidences of I, colon to f, or dot to f. So up to 2 decimal places, we will take the confidences, and it will be printed as a text. This line is basically to display the confidence value. Basically, confidence is nothing but it is your to display up to two decimal places confidence score. What is confidence score? Confidence score is nothing but it is accuracy of the prediction. Okay. Now rest all is all about. I'll just quickly do it. It's all about just drawing the rectangles properly. It's not playing an important role here. It is just drawing the boxes and all. You can simply copy and paste it for the other examples as well from here to here. This is just about, you can see that it is all about drawing the rectangles. Within the rectangle, it will display the label name, text, and the confidence score, and that's it. And according to that, your things will work. So your main code is this part, which I already explained you that it is trying to use this particular algorithm, which is YOLO. In that we have passed the whole weights, so you don't have to train the model. It is already a trained model, and we are just passing the image, and in return it is returning me the predicted outputs. Okay, so this layer outputs will be the various output, and from each output we are trying to get the detected region. You can see that, correct? This will be storing all your predicted outputs. You can see that layer underscore outputs will be storing predicted probabilities. It's saying model is not defined. Model dot output, where which line? Detection recognition. It is saying model is not defined. Model dot output. Okay, let me check why the model is not getting defined here. It is saying model not defined. One second. This should be model output now. No, it is okay. Has no attribute up. Confidence dot append. Which line? Confidences. This should be confidences dot append. I think the error is here. Yeah, this should be confidences dot append. Few more error. Invalid format specifier. Okay, so maybe I think this is due to, because in my case this particular will work. Either the first works or the second works. What happened here? Let me check. Okay, some error in text. Okay, let's pick my text part. Text equals to f. That is gonna be your formatted text, and this will be labels with my class ID. Okay, the curly bracket should close here, and then we should have one more curly bracket over here. Okay, now it is working fine. You can see we are getting the boxes, we are getting the confidence value. As you can see, whatever the confidence is there. So this will only able to detect those objects where the confidence value is greater than zero point 0.5. There are other objects as well in this case. Like you can see, this is a kind of a telephone. Maybe their confidence score is not high enough. That's why it is not able to predict.